Hello. So before we begin our study of thermodynamics this semester, I want to take a pause and share with you two quotes from one of my favorite thermodynamicists, Gilbert N. So although the quotes are over 100 years old, I believe they perfectly summarize the way I think and how I approach teaching thermodynamics. So without further ado, here they are. So the first one. There are ancient cathedrals which, apart from their consecrated purpose, inspire solemnity and awe. Even the curious visitor speaks of serious things with hushed voice, and as each whisper reverberates through the vaulted nave, the returning echo seems to bear the message of mystery. The labor of generations of architects and artisans has been forgotten, the scaffolding erected for their toil has long since been removed, their mistakes have been erased, or have become hidden by the dust of centuries. Seeing only the perfection of the completed whole, we are impressed as by some superhuman agency. But sometimes we enter such an edifice that is still partially under construction, then the sound of hammers, the reek of tobacco, the trivial jests bandied from workman to workman enable us to realize that these great structures are but the results of giving to ordinary human effort a direction and a purpose. Science has its cathedrals, built by the efforts of a few architects and of many workers. In these loftier monuments of scientific thought, a tradition has arisen whereby the friendly usage of colloquial speech give way to certain severity and formality. While this may sometimes promote precise thinking, it more often results in the intimidation of the neophyte. So from my experience as a student of thermodynamics and as someone that's studied thermodynamics, part of the challenge is thermodynamics can be really tough. It seems as if we end up with these final working expressions that come essentially out of nowhere. What is entropy? Where the heck did it come from? Why would anyone ever think about entropy or come up with this equation? Where does our first law energy balance even come from? Where does du equals TdS minus PdV come from? What's its origin? What does it mean? Right? And part of the problem I found as a student, and as I've kind of self-studied thermo over the years, is it's often just presented as if you should know, right? So we have these very hard topics that are just presented in a way that you should know. And you'll find in this course, I like to derive lots and lots of equations, right? And a motivation for that is when we get to that combined statement of the first and second law, du is TdS minus PdV, I want you to see where it came from, what it means, what assumptions went into it, what we can actually use that equation for. Okay, so we will perform extensive derivations throughout this course. When we get to things like Rayleigh's law, I will try my best to give you insight in terms of how did Rayleigh come up with Raylegh's law? What's its physical significance? What assumptions ultimately go in which Rayleigh wasn't aware of? Okay, and so I will try my very best to explain things, to take things apart, explain things, we'll derive things from nothing up into working expressions. And so if a lot of things that we do seem tedious and at the end we just get a final expression that we're going to use in, say, a problem, know that the reason for all that work is to try and show you where things come from. Okay? If anything is ever confusing in this class or doesn't make sense, please reach out to me and I will try my best to make sense for you. Okay? Thermo is a difficult subject. Okay? It is a difficult subject. So if anything's ever confusing, please just let me know. Okay, quote number 2. We've realized that the time may arrive when handbooks of thermodynamic chemistry will be placed in the hands of the craftsman, that he may follow a recipe or substitute numerical values in a formula of origin unknown to him. But for many years to come, the most useful application of thermodynamics to the arts will be made by those who in some degree have mastered the content and the methods of thermodynamics as a whole. And so one thing I'm reminded of when I read this quote is if I think about the modern day chemical engineer, if I'm designing a distillation column, right? I'm going to design that distillation column in a process simulator. I'll go pick up Aspen, I'll go pick up ChemCAD. They'll have all my thermodynamic models built in. They'll be able to perform the analysis for me. Okay? An interesting quote from Henry Keister, stat that I recall from Henry Keister when I would teach separation processes is that when these process simulators became mainstream, what they actually found is that design failure actually increased, right? Because what happened is people became too reliant on these computers, these black boxes, and lost insight in terms of what was actually happening in that unit, right? Actually being able to do sanity checks on the reasonableness of their models. And so when I told you the midterm exam and final exam are going to be conceptually based, they're going to be conceptually based because to me, these skills are incredibly important, right? Without doing calculations, you should be able to tell me things like, vapor pressure, does it increase or decrease with increasing temperature and why? You should be able to look at a given mixture and determine if, say, Rayold's law is going to be applicable or not. What I want to try and give you skills to do is to be able to walk through problems without doing any calculations whatsoever, because those are going to be incredibly valuable skills so that, yes, when if you ever need to use thermodynamics in the real world, design a distillation column in the real world, you will have a process simulator that can do all these calculations for you. But what I want you to do as a graduate from my class is I want you to not only be able to design, say, that distillation column in ChemCAD, but to be able to explain the thermodynamic models without doing any calculations, talk about what you would expect different, what would happen if I were to change the reflux ratio and explain why you would expect that to happen, so that as you run the simulation, you can really begin to make sense of things and understand what's going on. Okay, and so with that, we will be ready to move on to Chapter 1, begin to learn some material this semester.